Let's begin with our first steps towards creating a hydrologically correct DEM, in this case, creating a flow direction. And this, I would argue, is kind of one where it doesn't get a lot of respect. Flow direction, it has a lot of use. We're going to use it a lot, but we're never going to look at this map and say, oh, that's a pretty looking map, or do much with the output other than use it for something else. But it's very important that we run a flow direction. In the case here, we're going to do it first. What is a flow direction? It's very simple. What it does is it creates a raster or grid that shows the flow direction from each cell to its downslope neighbor. And so it's a local operation where it's only focused on what cell around me, around a particular cell, what cell is the lowest, or which one's going to have the biggest drop from what my elevation is, what my value might be. And let's go ahead and see this in an ArcGIS help file here, in which we have our input grid is our DEM, our elevation surface, in this very simplified raster. And then over here on the right is our output grid, the output of the DEM, and then running the flow direction operation is this particular grid here. Now, one of the things is it produces a grid of integers, and 8 of them in fact, that are all in the power of 2. And so the output is kind of like a code, as it says here, a direction code. And so all of these outputs is just for a given cell, what direction is the maximum drop? In other words, the idea here is you have water moving across the cell. Which direction will it flow? And the flow, of course, across the surface will always be in the steepest downslope direction, which we call maximum drop. How we calculate it? All it is the change in z value or elevation divided by distance, so rise over run, times 100 to produce a kind of a form of percent slope. So here we have, let's say, this particular cell. Let's say its distance to the other center here is 1, whereas the center for a diagonal is going to be more. And so that's going to be, in fact, 1.414216 times for each cell based on its resolution. So something to keep in mind when we have this whole formula in terms of change in z value over distance. You got to kind of keep that in mind when we have these diagonals because of the problems for center to center for diagonals compared to those that are right next to each other. Anyway, let's go back and try to understand what this is trying to show us. So here we have different elevation values. So of course 78 being the highest that I see, and it looks like 11 being the lowest. And so this is just essentially elevation. And so what we do here is then we identify from each cell which direction is the maximum drop. So let's use this particular cell here, this one with the value of 67. Which one of these cells around it is going to have the maximum drop? And it's going to be this one right here. 67 to 44 is the biggest drop. So 67 to 44. 67 to 44, that is a southeast, or let's say down and to the right. So in terms of the direction code, that would be a 2. So essentially what happens here is this is then in the output grid coded as a 2. Now let's go over here. Here we have 58. So 58, 53, oh, there we go. So 58 goes to 44. And so the direction of its flow, this assumption here, is going from here to there. And so that is here to there. That's going to be coded then as 128 for that particular value. So let's now take our DEM, our Marion County DEM. Let's use it as its input, as the input surface raster. We're going to create an output here that's called flow_direction1.img. We use the .img because it is a raster. In this case, we'll leave everything else as is, and we'll go ahead and we'll run the operation. And once again, no respect. So it really has no purpose. The map, all that, I blacked it out because it really doesn't have any use. All that's really useful here is to look in the contents pane. And in the contents pane, if we only had the numbers here, 1, 2, 4, 8, 16, 32, 64, and 128, we'd be good to go. But since we don't, look at the values. We got a whole range of values. They go on and on and on and on and on. And so essentially that's an indicator that, oh, Houston, we have a problem. Indianapolis, we have a problem. Here we have a DEM that is not hydrologically correct, a DEM that is not depressionless. And so we have sinks. So because we don't have just 1, 2, 3, 4, 5, 6, 7, 8 values over here in the contents pane, that's our indicator. So let me step back and explain, okay, well, what's a sink? What's a pit? what's a depression? And we have an assumption here, a very important assumption in these hydrology analyses, is that water is going to flow constantly down a slope, continuously moving across the surface. But when we have a sink, we have a problem. And so what happens here is we have a particular cell here. And so how sinks are identified is when you are a cell, an individual cell, and all the other cells around you are at a higher elevation, then your cell is identified as essentially as a sink. Now, if that's just one cell, typically what happens is the GIS will just bump you up to whatever might be the nearest in terms of its elevation to you. But when there's more than one cell that are adjacent to each other that are lower than the surrounding ones, then it's identified as a sink. So it's very important, is it does that kind of reduce the noise, because you got all these pixels. You could have a limitless number, not really, but you could have a huge number of pits, especially when we have very, 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 very good resolution in terms of our raster data. So conceptually, how this is shown in the GIS is why we run the flow direction is it kind of sends in an alert, because what happens is the GIS, it can't assign this particular depression, this particular pit, one of those 8 different codes, one of those different directional codes. And so it can't do it. So it just spits out some random number. And so when you have so many of those, that's then when you have a huge number of these sinks and these pits that we can find. Now, there is a tool in GIS, in ArcGIS, a sink tool, but it really doesn't have much use other than just identifies where sinks or pits are located. And so I went ahead and I did that with our flow direction, used that as the input in our output. I created a raster grid called sync.img, and we can see the results here. So all those little black little specks are areas in which we have sinks or depressions or pits in which we have more than one cell. If we just had one cell, we'd be eliminated because it's what they call noisy. It just has excess noise. And so when you have one cell, it's essentially, it's not really eliminated, it's bumped up to its neighbor elevation, kind of as a way to kind of say, okay, let's get rid of all this excess noise. And when you have multiple adjacent cells that are lower than the surrounding cells, that's when the GIS creates this particular file here. And these here, this sinks file, I mean, I can't remember, but it's a huge number, because what it does is it takes each of these individual pixels and gives it its own value. And so the number of values is quite large, as you can see, all these little black specks. Of course, we have some in the floodplain up here with Eagle Creek Reservoir, but we can see these pits all throughout the surface. And we can go ahead and zoom into our campus. You can kind of see what I mean here. And so these are groups of pixels here. If you really zoom in, it looks like one pixel, but it's actually groups of them here that then show the different pits here of the surface. And a lot of times this is inaccurate data, especially with LiDAR data. You're getting a lot of excess noise. But all we have is another operation that I'm going to do here. It's called a fill operation. And what it does is it identifies these sinks, but then fills them in. And it fills them in. And what it does is, going back to this particular demonstration here, is it fills it up to the nearest neighbor. So it's not going to go up to this one. I mean, it's a neighbor as well. It's going up to the nearest ones in terms of its elevation neighbor. So which one is its closest, and so that's how the fill operation happens. So let's talk about it. Let's talk about the fill operation here. And so the fill sinks in a surface raster to remove small imperfections in the data. So the assumption here is that those pits or those sinks, they represent errors in the data. And so if we did not do this, if we did not do the fill, we would have streams that wouldn't be connected. So we'd have kind of chaos in our data set. We wouldn't be able to create drainage networks and drainage basins and watersheds. And so you can see kind of why we had to fill in these pits and gaps, because what it would do is it would just create a lot of incomplete, disconnected data sets, spatial data, in which we really couldn't do much with it. So once again, we assume that we're working with this particular data, with particular elevation data in which water flows smoothly across the surface without pits, depressions, and individual cells that are going to change or alter that flow. So now when I'm running the fill operation, what I do is I put in our original DEM, and then I give it the output name fill.img. Once again, it produces a grid. And it's very important, it produces a grid that's very similar in look to a digital elevation model. And so the fill and the DEM, they look quite alike. However, if you look at the legend, notice the numbers, quite different in terms of those bottoms. That makes sense. We're filling in the bottoms, we're filling in the pits, we're filling in those areas, especially here, those pits and those lower lying areas, those depressions that are found down here where it's already at a lower elevation. And so I was kind of curious about this. I was like, wow, that's a huge difference there. I didn't know we had that much difference in terms of our topography in the high point and the low point here in Marion County. And so what I did was I said, okay, this is something I want to figure it out. And so here's an example of how you use the raster calculator to use a set null statement. And so what this is saying, okay, we have this Marion County DEM. What I want to do is I want to essentially all values that are above 400 in elevation, I want them to essentially be null. I don't want them to be zero. I don't want them to show up in the map as a color. I just essentially want them to be null. I want them to show up as invisible. And so that's what this is saying, is set null, Marion County DEM, those places, those cells that are above 400. Anything else, anything essentially between 269.44 and 400, I want to make that 1, make that something which I can actually see on the map. And so what I'll do is then I'll create essentially a new output raster that shows where is that super duper low point, that huge amount of low points, I should say, within Marion County. And after you run that raster, here's the result. This tiny little segment here is essentially incorporates all of the 269.44 to 400 elevation values that are shown anywhere in the map are shown right here in this particular area. What's there? Zoom in. It's a quarry. So that's where we have a huge limestone quarry, which of course they're digging deep, deep, deep down into the ground. So it's a man-made elevation pit. So what we have is 465 and 37. Those of you familiar with this particular area, on your way maybe to the airport, if you're a South Sider, you'll see a huge, would say almost looks like a mountain. And so some people think it's a landfill, which it probably is a landfill as well, but also all the debris, which is kind of scooped out of this pit, is collected there. And so over time, this sucker's gotten taller. And so essentially what we've done is we use this particular tool to identify where in Marion County we have this super duper low point. Now let's go back to our flow chart. In our flow chart, okay, we've done our operation. We've identified the sinks by doing that flow direction. So now what we need to do is we need to run the fill, and we did that. And so we filled in all those sinks, all those depressions. Next step is we need to go back and do another flow direction to make sure that we actually did the fill. And so what we do then is we run a fill direction. And so now we're going to use the raster that we just created. The one that we just created is essentially the filled DEM. The DEM that no longer has those depressions. And so the output flow, now we have one that's called flow underscore direction 2. That's going to be important because we're now going to use this one, this direction raster going forward. The first one, it's useless to us. It doesn't have any use to us. And we're going to go ahead and run the operation. And once again, we could care less about the map that's produced. All we care about is what does the contents pane tell us. In this case, the contents pane has 1, 2, 4, 8, 16, 32, 64, 128, which correspond to the 8 numbers here from our directional coding. So essentially, we've done our objective here. We now, once we've seen this flow direction output, that means we've got ourselves our triangle, which is our symbol for our hydrologically correct digital elevation model, or our depressionless DEM.